Hello, doctor. Can you hear me?
Hello, I'm here. Yes. Hi, is this Arash?
Hi, I'm Rash.
How are you?
Thanks, I'm good.
Good, thank you.
Having-
Sorry, it took me a sec. I just went to the Google Meet and I realized that you had sent me the password. You
Yeah,
see, by the way?
sorry.
Oh, do you see me?
No, not yet. There's on the top.
Now you see me.
Yes, yes. Now we can see you. Great,
Great.
great.
Okay. What is this platform?
It's something that we build ourselves
Oh, nice.
because the university it's hosted by the university, but because Meet and Zoom and other platforms don't give service to us, we have to build something for us.
Oh, okay. Well, you built a pretty good one. So this is great. Awesome. Let
Okay.
me. So, how much time do I have? 1 hour or an hour and a half?
1 hour and a half. We schedule for
Okay.
1 hour.
I think I'll try to have the last for questions. So I'm gonna. I think I'll talk for like an hour, but maybe I'll go for this over. I don't know.
Okay. That's okay.
uh, okay. Perfect. Great. Whenever you want.
Great. If you want to share your screen or something,
Yeah.
there.
Let me share my
Yeah.
screen.
Okay,
Let's do a little test.
yeah. We have it now, but
Do you see? Is that
let's.
the right logo for Sharif?
Oh, yes, yes.
And
That's
am
good.
I pronouncing it correctly, Sharif?
Yes,
Sharif.
Sharif.
Okay. Let me just get one thing. 1 second. Uh, okay. And is there a chat or something for people
Oh,
to?
yes, there are. If you have the screen for this platform on the left bottom, there's a chat window. People can
Oh,
chat and ask
there it is.
question or answer to something that you ask them.
Okay.
And people also can open their webcam and ask you verbally if they have question.
Okay, fantastic.
Okay, I
How many
can give.
people are there?
Right now there are 14 people, but I think
14.
people,
14.
yeah, yes, yes, they're
Okay.
coming. About 50 people sign up for the time.
Nice. Okay,
Great,
perfect.
great.
Whenever you want.
So
Yeah.
we can start. Okay, welcome everyone. We are very excited to have Dr. Luis Serrano with us today. We all learned from you from your academy a lot. I think
Thank,
everybody here learned something very, very much from you, and we are very
thank you.
excited to have you with us for this wonderful time. Okay, the stage is yours, and we are very much looking forward to
Thank you so much. Salam, Shetori,
it.
Huban.
Salamat.
How's
Okay.
it? How's everybody doing? I'm very happy to be here at Sharif and talking about reinforcement learning. So thank you very much for the invitation. Sharif, I've never been, but it's one of my favorite places because everybody I've met from there is a genius. Such a great place. In particular, my hero. I don't know if you've heard of Maria Mirzakani. She's from there. She's like was a mathematical hero of mine, both in high school in the Olympiads and also in the she won the Fields Medal, um, the top prize of mathematics. So anyway, very happy to be here. And so this is what I've done. I think this crowd is very expert in reinforcement learning, um, which means you can help me out if I get confused. I have 6 videos on reinforcement learning in my channel, which if you haven't seen it, I'll tag it here because basically what I did is I I attached all 6 things and then removed some things because this is like 4 hours of material. But I encourage you to take a look at them for more details. I'm gonna kind of like skip over things. Um, we have the chat right here, so if I'm going too fast or something, let me know. If I'm going too slow, you can also take hey dude, we know this already. So let me know as well. I kind of always get like to get help from the crowd. If you want to open your mic and talk, by all means, this is for you. This is your time, and you know, if we end up in going in a tangent and talk about something different, then that's fantastic. So I'm gonna start slow, and I know you know reinforcement learning. I'm gonna start sort of introducing it more for me to wake up and us to sort of like get in the same page. So this may sound repetitive, but I'm just gonna put it in in the way I look at it. So I'm gonna start with grid world. Grid world is my favorite example of reinforcement learning. and it's basically a game. Do you see my mouse, by the way, if I move the mouse? Yeah.
Yes, yes, we can see.
Okay, perfect. So in grid world, I have my space of moves, my environment. This grid is the environment. This is the agent, right? And I have a price here, a lot of money. I have some money here and a dragon here that will eat you. So the game is to basically get to the money. This is +5, this is +4, and this is -1. If you get by the dragon, those are the rewards. Um, and then I have some blockage walls here that I can't cross. And the idea is that the agent moves around, and if it gets here, you get a +4. And if it gets to other places, you end up, the game ends when you hit, for example, the -1 or the 5. And the idea is to teach the agent to play as well as possible. So we're going to introduce some terminology. As I said, you probably know this terminology, but every single place where the agent can be is a state. So not the walls, but the winning and the norm and the intermediate places are all states. Actions are the things I can do. So I can move to the top, to the left, to the right, or to the bottom. And then technically, I can do this. Um, I don't know if they did this in Iran, but I felt like like an agent in reinforcement learning during COVID, because the supermarkets had these arrows in the ground that you could only walk in some direction, and I did feel a bit like an agent who was following the rules of the of walking around in the floor. Obviously, we can remove the ones where you crash against the wall, because that'd be pointless. So these are the available actions. So every state comes with a bunch of actions I can use. Um, then we have the values, and the values is this is the sort of when things get interesting. The value of this spot here. Let's say that it costs one unit to move one spot. Okay, so if it costs 1 to move one spot, and here I gain 5, then here I have 4, right? Because it took me 1 to move, and the value of that is 4. So it's basically the best I can do from there. So who can help me out just to be in the same page? What's the value of this box over here? You can yell it to the microphone if you want. mm, -1. I think it's a little more. What's the best I can do from here? Oh, remember, yeah, I think it's 2, correct? I think it's 2, because when I walk here, and whatever thing I do, I'm going to have a 4 here, a 3 here, and a 2 here. So the value is 2, right? What would the value be here? Who can help me out? As well, 2. Very good. Very, very good crowd. Yeah, because you could think that you want to walk all the way to the 5, and then it'll be a -4. But if you're going to spend so much money going to the 5, you might as well spend less money and go to the 4, and then have a 2 here. So it's not trivial what the value is. You have to have a good strategy. Sometimes it's even better to walk into this -1 than to spend all this money walk into the -4, into the +4. So basically the values, you just take the maximum of the neighbors -1, and then sometimes you have to visit a cell twice to revisit, but eventually you can get them all. And I would just say, yeah, take the neighbors of the 5, that's 4s. Take the neighbors of 4s, label them 3s. The labels of 3s, label them 2s, then 1, then 0, then -1, and the labels of the -1s are -2. So if you're here, you're better off walking into this dragon here than taking all this time to make 4. Okay, so now we go to policy. Okay, so policy is basically what's the best place you should move. So in principle, if these are the values, the policy is very simple, right? Where should I move if I'm here? Well, I should probably not move to the 0. I should probably move to this 2 or to this 2. Doesn't matter which one, right? So if I'm always pointing at the biggest value around me, that's pretty good. That's a policy, right? And you can have a policy that gives you options. So, well, here, for example, I would say your policy is to walk to the highest value around you, and that does it. So here's a policy. For example, if you're here, you move down. If you're at the 0, you can either go here, or yeah, pretty much that's all you can do. If you're here, you can do 2 things, right? You can do to the +5 or go to the +4. So policies can give you more than one option, but this policy is deterministic, all right? Normally, you wouldn't want a deterministic policy that tells you exactly what to do, even if it gets you to a better value. Normally, you would want a stochastic policy. A stochastic policy tells you, you know what, you should, with 90% probability, walk in this direction, and with 10% walk in this other direction. And then maybe you don't get, and here, so for example, you would say, I'm more likely to walk towards the bigger one, but I have a small probability to walk to the small ones. And the reason for that is that you are able to visit more squares because we're finding stuff out. So it's better to visit as much as possible, right? It's better to visit as many places as I possibly can, in order to get to know more about the environment. So far so good, right? Like so far there's no science here. Like we just pick the largest value. We just always try to do better. Why do neural networks come into play? They don't seem like they have a place here. Because if I can just find my perfect values and my perfect policy, then I'm done, right? Well, the problem is that in order to find this policy, I have to play the game a lot of times and visit a lot of squares. That's expensive. And here maybe I'll be able to do it. But if I have a huge grid, billions by billions, there's no way I can visit everything multiple times in order to come up with the best value. So I don't know what to do. So what we do is and sometimes even worse. For example, if you have a robotic hand or something that has infinitely many states, I can't visit infinitely many states a bunch of times in order to find the perfect policy and the perfect value. I can't do that, right? So we use neural networks. And why do we use neural networks? Well, think about this. If the value of this square is some number, the values around it have to be similar. There's just no escape. You can't have a value like here you do amazing, but if you do one step, you do terrible. No, the values are similar. And the values of the neighbors are similar, and the values of the neighbors are similar. And in the same, if a value here is very negative, the values of the neighbors are probably similar. So I don't need to find all of them. If I know a few of them, I can sort of propagate the others continuously. And that's the feeling that a neural network has. A neural network says if your value with this input is 10, if you put neighbors very close, you'll get 10.1 or 9.9 or something like that. So like you're basically always, you have some kind of continuous function. And so we use a neural network. In this tiny grid case, we would just put the coordinates, right? X and Y, the coordinates to the neural network and get the value over here. And if you train it to hit certain spots really well, then the neighbors, you're confident that you get somewhere close. So this is the first object of today, the value neural network. Remember this, this is gonna happen a lot of times today. There's a neural network that estimates the value of a cell, the score, right? And in the same way, the policy has the same property. If my policy here is these four probabilities, the policies around are probably similar. If here you should go up, from here you should also probably go up, right? Like so like I can also have a neural network that determines a policy. In this case, it's a slightly more complicated neural network because given the two coordinates, you output four things, right? You output the four probabilities of going up, down, left, and right. So four probabilities that add to one. Um, quick question: how familiarized are you with? I know you're familiarized with reinforcement learning. How familiarized are you with neural networks? Uh, are we all good with that? Send me a thumbs up. Um, Always happy to talk about them more if necessary. So in summary, basically we have a values neural network. Sorry, we have a bunch of values, but this is too much. This on the left is too much to calculate. It's too much to ask. So we have a neural network that approximates them, and it does a pretty good job. As you can see, this is pretty close to this. It may be off in a little bit, and the more we train it, the better. But we'd rather have this because we can train this thing on the right very quickly, whereas this takes us too long. So we have a neural network that approximates the values. And the policy neural network, same thing. We have our perfect policy here, but instead we want a neural network that will kind of approximate our policy pretty well. May not be perfect, but pretty well. Um, and the reason is that we want something like this is because this is deterministic. It only exploits. It doesn't allow us to explore. It just goes straight to the answer. Whereas this one allows us to explore, and you may get wrong answers sometimes, but you at least visit more places and are able to train them better. So in principle, today we're going to have the two neural networks. The one that approximates the values, the value neural network is always going to be pink, and the policy neural network is going to be always going to be this sort of bluish greenish that approximates the policy. Okay, um, and we have to train them both. So we're going to talk today about several algorithms that are able to train both the value neural network and the policy neural network, um, and they um, and they are able to sort of train one, train the other one at the same time. And what we're going to see today is PPO, DPO, and GRPO. Okay, they're all different ways of doing it. Some better than others. But let's go to large language models. So let's. By the way, I'm going to switch topics. Any questions about reinforcement learning? Feel free to ask any questions. All good. Perfect. So let's go to transformers. So everybody knows, I think you probably all know this, but let's just get on the same page. When I see a transformer, I think of a transformer of Optimus Prime, which generates language, generates text. This kind of, I'm gonna be honest with you, this kind of drove me crazy when ChatGPT happened, and we were like, "Ooh, this is amazing! We finally have that chatbot that everybody's been wanting for so many years." And it talks one word at a time. I really thought that they were going to do something different. I thought we are going to have something that writes a bunch of text and then uh, corrects it a little bit. And but the thing that talks one word at a time still blows my mind. But it talks really well. But if I wanted to say, if I say something like "Hello, how are you," it only comes up with the next word. So it's kind of like autocomplete, but it does it well. Um, so if I want to say, for example, write a story, well, the thing is going to write, it's not going to write a story. It's just going to come up with the next word. And the next word is, I don't know, let's say once. It'll just say the next word after for your story is the word once. That's all. And so if you wanted to write the story, you have to go back, put the one in the input and say, what's the next word after write a story once? And it goes, probably upon. And then, okay, what's the next word after write a story once upon? Be like, you probably want the letter A, and so on. And that's how they write it. Um, I can talk more about transformers if you like at the end, if you want to have any questions. But this is pretty much all I'm going to say. They get trained in a particular way, which is you basically train a big neural network with all the internet, all the books, all the PDFs. But that's not enough, because it still has to do things properly, right? The internet is not a repository of questions and answers. The internet is just a bunch of text that pretty disorganized. So you need to give it some curated data sets. For example, a question answer data sets of chats, data sets of or where you give it an order and then it does the order so that it starts learning to behave like a proper chatbot. And that's still not enough. So that's not the end of the story. We need to fine tune them, and a way to fine tune them is using humans. Okay, so what you do is you would, for example, let's say you get a prompt, "What's the capital of Sudan?" And it goes, maybe Cairo. Then a human will come in and say, "Nope, it's Khartoum," right? So like it would basically a human has to come in and make the computer play a game and have the computer and have the model basically try to win at this game, which is pleasing the human. Okay, how does it do it? Well, let's say you ask it what color is the sky. So it goes, let's say it answers blue, red, and banana. Okay, so then the human will say, okay, I like this one more. And then this model is now the agent that is trying to play the game of winning at pleasing the human. Okay, that's where reinforcement learning with human feedback comes in. And so how do we turn it into a grid? Because I like to see, I have this thing when I see reinforcement learning, I need to imagine a grid. If I don't imagine a grid, I don't understand reinforcement learning. So I had to wrap my head around this as a grid. Well, a grid can just be made, sentences can appear in a grid, right? Because I can just start it here, so token for starting, and then each direction is a word. So you add the word what, the word color, the word is, the word the, sky, and question mark. And so in each neighbor of a sentence is the sentence with an extra word. Obviously, it's not going to be a grid, but just wrap your head around it as a grid, and then we're on the same page. And the agent, as the walks through the grid, is forming sentences. So here, what color is the sky? I have three ways to go: blue, red, or banana. And so how does it know where to go? We're exactly a reinforcement learning scenario. It says it can go in either direction, and each one gives them some points. And the points come from what the human gives it. So the human says, I think the best solution is this. This is gold medal. The next one receives a silver medal because, maybe the sky is red one day in a nice sunset. And the bronze medal, unfortunately, is for banana because the sky is never colored banana. Um, so it just gives it points: 3 points for blue, 2 points for red, and 1 point for banana. And that's the idea. That's how we play the game. The human decides. The human decides the points. Okay. And so the value neural network is basically the one trained by the scores of the human. So in other words, the value neural network. Check. This is very important. The value neural network is supposed to mimic the human. Okay. So when you think of the value neural network, is a network that is trained to think like the human, to emulate the scores that the human gives them. This pink thing is the human, okay? Um, and yeah, and then that's the idea. And the policy neural network is the one that gets trained to go in the direction to generate the next word, okay? The policy neural network is the one that gives us the probabilities of generating the next word. And it's supposed to output a big probability for blue, a medium one for red, and a really low one for banana. So in other words, if the value neural network mimics the human, what does the policy neural network mimic? Who can help me out? What's the policy neural network? Let's see. Any thoughts? Exactly, Omid, good job. The policy neural network is exactly the transformer. The policy neural network is the transformer. So we have two neural networks. See how, like in reinforcement learning, we have the value neural network, the policy neural network. And when you do that with RLHF, the value neural network mimics the human, and the policy neural network is exactly a transformer. ChatGPT is the policy neural network. DeepSeek is the policy neural network. Okay. So now that we have our two players, the human and the transformer, then we can train them both at the same time. Sorry. Uh, so obviously we have longer paths, right? If I start with roses are red, I'm not gonna just do one sentence, right? I could go roses are red, violets are blue, and then end token. The end token is the token that ends the sentence. I could say roses are red, violets are humans too. Why not? And I could say roses are red because they like ketchup. And then the human would just rate this 3. Oh, sorry. Oh, I'm sorry. Uh, and the human would just rate these 3 things, right? It would rate one of roses are red, violet. This maybe would be the highest. This would be the next highest, and this would be the next highest. So in general, if we have 3 possible responses, right? Like I start here, and this is one sentence, this is one sentence, and this is one sentence, and response 1, response 2, and response 3. Then the sentence is a whole path. And then the human will rate the 3 of them and will say, you know what? I think response 2 is the best one. The green is the best one. Then the yellow is the next best one, and the red is the next best one. And what I want to do is basically these scores are the values. So that is used for training the value neural network. Here I have my value neural network, and I make it learn those three scores, right? See what I did there? I take these three scores and I make the neural network learn those three scores to improve the scores. And then what do I do with the policy? Well, every arrow that took me to the good response, check this out. Every arrow that took me to the good response, I want to increase its probability. Every arrow that took me to the okay response, I want to kind of keep like that. And every arrow that took me to the bad response, I want to decrease the probability. Okay, so this is information that I give to the policy neural network. I tell it, okay, increase all these ones and really decrease all these ones. And these ones, I guess, whatever, if they're high, make them low. If they're low, make them high. Keep them medium. And we feed that information to the policy neural network. So the policy neural network and the value neural network get stronger. Okay. With every time the human makes a rating, you're giving the value neural network information and the policy neural network information. Obviously, I'm too optimistic to think that language fits in a grid because you can put many, many words after one word. They look more like a big universe with a lot of every point is a sentence, and points are connected by an arrow if from one sentence you're adding a word to the other sentence. So for example, from hello how are you to hello how are you good, you have a pretty strong arrow because good is a good word for that. So if I have what color is the sky, the path, what color is the sky is blue, is a pretty strong path with high probabilities. And the path, what color is the sky, banana purple monkey dishwasher, is going to be a pretty weak path with pretty tiny thin arrows, right? So the idea is in this big universe where all the bunch of sentences are flying around, it's as big as the embedding has dimensions. So it's 1,000 dimensions or something like that, 1,024 or something big. um, you want to basically find the thickness of each one of the arrows and make the thicknesses perfect so that when you walk through the thickest arrows, you get sensible sentences that answer your questions. That's the idea, right? To really enhance these arrows. Um, and so what you would do is you take the value neural network, and if this sentence got a high score and this sentence got a low score, then the policy neural network, you basically tell it, make these arrows thicker, make these arrows thinner. So this is basically a pictorial representation, but we'll get into the formulas. Don't worry. And we're gonna get through PPO, principle. I never get these acronyms right. I think PPO is Principal Policy Optimization, but please correct me if I'm wrong, because then DPO, the P is not a principal policy. It's like preference or something. I think they do this to confuse me. So here is PPO. Okay, PPO says you're going to train the neural network, and this is the loss of the neural network. This ugly thing, E of V, blah, 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 blah. And when you train the policy neural network, this is the loss of the policy neural network. It's pi blah blah divided by the other pi times something. I see this and I go, well, it's ugly, but it's not so bad. It's not so bad, I promise. Let's start by training the value neural network. So again, we're doing PPO, right? Um, so here's the main idea for training values. This is where numbers come in. Let's say that I have a value of 2. Let's say that, sorry, let me start again. I have a box here, and the neural network tells me that the value for that is going to be 2. Okay, the neural network says 2. The actual value, I took the work of calculating it, and it was 5. And I calculated it using a path and trying to get to what the human said. The human said it was a 5. So we have a gain of 3, right? We have a gain of 3. So I'm going to give that information to the neural network. I'm going to take 5 minus 2, so the actual value minus what the neural network said, and I'm going to get to increase these 2. So I'm going to take that 3, put it in the neural network, and say you need to up this by 3, and put it in the derivative in the loss function, and then the neural network spits out something bigger, like a 2.1. And if it's the opposite, if the neural network says 5 and the actual value was smaller but 3, then you still do that subtraction, and you have not a gain but a negative gain, and you put that in the neural network, and you get a smaller value. And obviously it's going to be a small change, but it happens a lot. So in summary, what happens is this. Let's say that this is my value neural network, okay? And I'm here. And I walked based on the policy. So my walk isn't perfect because it's based on a not yet fully trained policy neural network. It doesn't matter. I just still trust it. I trust it enough that I use it to walk like here. And I got to 5. Okay. So my actual values are going to be 5, 4, 3, 2, 1. Um, like we said at the beginning, right? And so this is what I want. These are the ones I want, and these are the ones I have. Okay, check this out. The values that I want are this, because I actually went through the pain of calculating them using my final value. And the values that I have are these ones. So they're pretty far off. So how far off? I'm just going to subtract these. Okay, I'm just going to subtract them and square it, because we do that a lot in machine learning, right? You subtract and square. And I get, this is what I get for my subtraction squared. I take the average, because it's a long path. I take the average. And so I divide this by 6. Okay. And so my error here was 3.36. Okay. That's the error function for training the value neural network. And here I have, that's my loss. And that's exactly what the formula said, right? The formula looked ugly, but that's exactly what the formula says. And I use this loss to train my value neural network. And so basically, what I do is I with the new neural network, I would output something that's closer to the actual values, right? And so if I have different, I do that for different paths. And if I do that for different paths, then I'm going to really be training this value neural network. So in other words, I I take a point, I walk until I get to the values, I take the difference of those values and the values that the neural network gives me, and that difference squared average is the loss of the neural network. And that's exactly the formula, right? Because the formula says this. Now this is ugly, but this is exactly what we did, because the expected value is when I take the average, 1/6, right? This v theta of st is exactly this, right? Because these are the values given by the current parameters theta of the states. So the value of the states are exactly this. And I subtract the actual rewards. So these are the rewards given by the human, and I squared it. Okay, so this formula, if you remember one thing of PPO, this formula is exactly how far are you from the values. And basically, we use this loss to train a neural network the way we use a loss to train a neural network in general. Okay, we walk around, and every time we make these parameters a little better. Any questions so far on how to train the formula for the game? All good? There's a good question here by Omid. How my neural network values are valid if we're trying to mimic throw the reward we get using our not optimal? Yeah, that's a very good question. We don't have an optimal policy yet to walk around, but every step we train both. So I'm going to tell you now how to train the policy neural network, and every little step. Oh, Omid is actually guessing what's next. Why do we need 2 neural networks? Couldn't we? I think you just discovered DPO, Omid. Because yes, you do. You can do this just 1 neural network. Um, so I'm going slower. Right now we're doing 2. Um, but hold that thought, Omid, and we'll talk in a bit. Okay. Let me see. Let me see. Where were we? Okay. So we told you how to train the value neural network. Let me show you how to train the policy neural network, and that's with a surrogate. So this part is fully understood, right? This part of how to train the value neural network is understood. And tell me if it's not, please put it in the comments and or open up the mic and ask me. Now I'm going to show you how to train the policy neural network. Okay, the policy neural network. And this is something that's going to happen later as well in GPO. Why is there a probability divided by another probability? That drove me crazy the first time I saw it, because dividing by probabilities is weird. Dividing by probabilities is very strange. I don't feel comfortable with that. So until I saw it and I realized, why is it that you're dividing by a probability, I was okay with it. But this bothered me for a while. Let's say that you're walking around your neural network and the policy says your probability for making this step is 0.2. Okay, this is given by the policy neural network, which is yet not super trained, but that's it. And then you use the value neural network, and the value neural network, you use it to estimate the values of the two spots. In particular, let's say that the value neural network says this is a 2. But when you calculate the actual value with the human reward, you get that it's a 5. Okay, so we need to improve this probability, right? Because this probability tells us that you're walking into a 2, but you're actually walking into a 5. You got more price. So therefore, we need to, first of all, we need to increase the value, but that's the job of the loss function of the value neural network. So we took care of that already, right? Now we need to improve this probability, right? They're both hand in hand being trained at the same time. So what do? We're going to train this probability in the following way. We're going to come up with a loss function. First of all, let's say, how do we get this 5? I'm kind of combining the language thing and the grid thing, but bear with me. And if anything, let me feel free to ask a question. How do we get this 5? Well, let's say we walked all the way until we found a 13, and that was the price, and we backtracked it all the way to 5. Okay, so this is given by the policy neural network. We walked using the policy neural network until we hit a price, which is the human gave us a score. And now what we're going to do is we're going to calculate the gain. So we say 5 minus 2 is 3. So I need to get this 2 all the way up to a 5, but I actually need to get this 0.2 all the way up to a higher 0.3 maybe. What I'm going to do is I'm going to use that gain to feed it into the policy neural network. Okay, so it's a positive gain, and it means I need to both increase the value and increase the policy, because I got something good, right? I need to increase the probability of the step to, for example, 0.3. Okay, so I'm going to tell you how to increase it. And also, if I'm going down, then I need to decrease it, right? If the value neural network says 1, but the actual value was 1, sorry, it was 6, and the actual value was 1, then my difference is -5. So this is a negative gain. Okay, so I need to tell the neural network to decrease the value and the policy neural network to decrease that probability. So this difference between the actual value and the predicted value is what tells me if I should increase or decrease the probability, right? So what we're gonna do is updating, and we're gonna use impulse or momentum. And this momentum, a physical version of momentum, is where this ratio of probabilities appear in a weird way. So check this out. Let's say that a kid is running. Okay, the kid is running in one direction, and we have two scenarios. If the kid is running in one direction with some velocity, let's say 10, and I want to push the kid, then when I push the kid goes in a higher velocity, right? It went from 10 to 20 because the kid was running in direction, and I pushed the kid in the exact same direction, so it went faster, right? Without tripping the kid, right? Like I'm a gentle push, but I make him go faster. Now, if the opposite is the case, if the kid is running in one direction and I push the kid in the opposite direction, so if the speed is, let's say, -10 because it's in the wrong direction, and I push the kid in this direction, then I'm not going to go all the way to high speed. I'm just going to reduce the speed. Okay, so that's the idea. if I push something that's going in the forward direction, I push it a lot. But if I push something that's going in the backwards direction, then I don't push. I push it, but it doesn't go so fast. So hold that thought. Okay, hold that thought. Um, and so I end up with a higher velocity if I push in the direction that's going than if I push in the opposite direction. Okay. Um, that's so hold that thought. Okay. So now this is the idea. If my probability, I look at a certain probability and I look at how quickly has it been growing. Has it been growing steadily, or so if it's been growing, if the probability got up in the previous iteration and then up again and then up again and then up again, it's like the kid is running in the same direction and I want to make it up, then it should go up by a lot because I have confidence that this is a high probability. It's been growing for a while and my gain was positive, means that the gain is the value minus the predicted value is positive, then I should push it a lot, right? I should push it a lot because I'm confident that it should keep growing. It's on the growing direction. Whereas if the probability has been decreasing and the gain is positive, well, I shouldn't bring it up that highly because it looks like it's decreased. All of a sudden, I get information that says, no, 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 it should be growing. Well, I'm not that confident that it should grow so much because it's been decreasing. I want to continue the trend. You know what I mean? So this is like if the kid is running in the backwards direction and I push it, it doesn't go that fast. Okay. So if I have impulse, then I go faster. But if I don't have impulse in that direction, then it grows slower. That's the idea. Okay. So now let's put some numbers. This is scenario one and this is scenario two. Scenario one, let's say that in my iteration 100. Okay, I've been growing this, training this neural network for 100 iterations, and some probability happens to be zero 0.4. Well, if the gain is positive on both cases, let's say that the gain is 10, which means the difference between the value and the predicted value is 10. So it means I have to grow this 0 0.4 because I have a huge gain here. I need to grow this probability. By how much do I grow this probability in iteration 101? Well, not always by the same, because I look at the previous iteration 99 and I checked, is the kid running in the same direction as the gain? Like, did it go from 0.2 to 0.4 and then continue growing? Or did it go down from 0.8 to 0.4 and now I want to grow it? See, these are different cases, right? Because here, I want to grow a probability that has been growing. Whereas here, I want to grow a probability that has been decreasing. So I want to go in the wrong direction as the trend. And so therefore here, I really want to grow it because it went from 0.2 to 0.4 and then all the way to 0.8. I really want to grow it. Whereas here, I'm not that confident. I want to grow it, but not so much because it's been decreasing, right? If that's not clear, please put it in the comments. But that's a crucial idea. And in reinforcement learning, I'm gonna dare to say that maybe I'm not right, but that every time you see a divided probability divided by the other one in reinforcement is because they're trying to do this momentum game. They don't tell you the papers. They don't tell you. They just put it there and they go, "I'm a genius. This is what I came up with." And it's like, no, what you're doing is following a momentum. Okay. Um, so that's the idea. And how do we take care of that? Well, using the ratio, right? The surrogate objective function is the ratio, because when I take the 0.4 divided by the 0.2, I get a high number, right? I'm dividing this number by this number. So if it's growing, then this ratio is big. Multiplied by the gain is bigger, right? 20 is huge. I multiply the gain by the ratio of the probabilities. Whereas look at what happens here. If I take the 0.4 divided by the 0.8 and multiply it by the gain, then I get something not so high, because this 0.8, the fact that this thing wasn't growing, means this is a small number. So my gain gets tampered with. Whereas in this one, my gain gets increased. Okay. So you have two things. You have how much is the gain, which really matters, and how much is the ratio between the probability and the previous one, which tells me the momentum. Multiply those two and you get something big if you want to grow it in the same direction, and small if you want to grow it in the other direction that's been growing. And I'm not going to do scenarios 3 and 4, but imagine if this number was negative, if the 10 was a negative number, then it's the opposite. If you're going under, if you're decreasing, then this decreases less than this would decrease. So I'll let you, feel free to like screenshot this and work out the other two cases where the gain is negative, and convince yourself that when the gain is negative, the same thing, the opposite happens. If you're going down, you go more down, and if you're going up, you go less down. Is that clear? Feel free to throw the occasional thumbs up or thumbs down if you're if it's going well. Okay, excellent. I love the thumbs up. Thank you. um, all right, so that's the idea. I made a big deal of this because it happens so much in reinforcement learning with language models, that you have this little tricks, right? This little tricks like a range of probabilities multiplied by the gain. Okay, so that's the idea, right? And that's why we have this pi theta of action given the state divided by pi theta old of action divided by state times the AT. This AT is the gain, right? Like this this these things are the current probability. This is the previous probability at iteration 99, and this thing over here is the gain. The gain is the difference between the things, the difference between the value and the predicted value, and that's where we get the policy. Okay, so this is the loss that we're going to use to train the policy neural network. Okay, I think that's the most math we'll see today, because everything else just repeats. And that's the idea. So this is the one that you use to train the policy neural network. Okay, what do we have now? Sorry, I did a huge copy paste, so I don't know exactly what's coming. So let's say we have the transformer, right? And we put the entry, which is once upon a, and then the outputs are, let's say, time and banana, and the human rates them. And then the idea is that it gives them a score. Okay, so with that, we train the policy neural network. So by the way, now we're going to learn DPO. So DPO is discrete preference optimization. And I'm going to answer basically Omid's comment, which is very good, which is why do we need two when we really just training this policy neural network, right? Like the value neural network is there as a helper, right? But why don't we just put everything in the policy in the policy neural network? Why don't we just do that? So as we said, this is the transformer model, and the one that talks. And this is the reward model, the one that guesses how the human rate inputs. And we're gonna do that. We're gonna just worry about the transformer model. But these ones train each other, right? With this one, I can use to train this one, and then back and forth. And this game of training both at the same time is very common in RL, right? You're training both. You're training the actor and the critic. This is the actor, and this is the critic, right? This is in a GAN, this would be the generator, and this would be the discriminator. You always have the student that's learning to do better, and the teacher that's telling the student how to do better. But what we're gonna do is we're just gonna focus on this one. So PPO has this log loss. I'm not gonna get into details, but this I have on the videos in more detail. But basically, a PPO has this. If you work it out mathematically, you get this loss, where you have this path coming from the transformer model, from the policy neural network, and these rewards coming from the reward model. As you can see, you're trying to. This formula basically says the reward of the winning word. The winning word is time, minus the reward of the losing word, which is banana, given x, which is the input. You're trying to maximize this using the steps that come from the path given by the transformer model. So this is a pretty basic way of seeing the loss of PPO, right? But unfortunately, it uses this and it uses this, okay? So what we're gonna do is we're gonna try to only use this ones. So we're gonna do try to remove the reward model and do direct preference optimization, which basically, yeah, removes the reward model and only uses this one. And we're going to get a loss function that is this. And as you can see, there's the ratio of probabilities, and there's the stuff that we normally use. And this one is better because check it out. All of it depends on this one. There's no reward here. You see, they've managed to remove. I don't care what this formula is. It's a big blah blah, but it only depends on the transformer model. It only depends on this blue green network and not on the purple one. So we managed to remove the purple from that equation. Now the question is how. So here's the idea of the DPO main equation. This part over here, don't worry about all the details. This part over here maximizes the rewards. And then there's this other, which is basically the input is once upon a, and the output is time and banana. So this maximizes the rewards by picking the right answer, by picking the answer time. And this is a new element that's coming into play that is also very common, which is this prevents the model from changing too drastically. I'll get to that. I'll get to that soon. Okay. But the idea is that we're gonna take this R and remove it, because this probability pi is nice because it comes from the neural network, the policy neural network, but it's this R that I want to get rid of. I want to get rid of it by turning it into a probability. Give me a thumbs up, thumbs down if something's not clear, and I'll elaborate more. But the idea is that I want to get rid of this R because I want to train everything with the policy neural network. So for that, we use the Bradley-Terry model. And the Bradley-Terry model is exactly the softmax. And this is KL divergence, how to measure how two different models are. I will get to KL divergence in a minute. So I basically get to turn this formula into only a formula of the policy neural network. And this is theta is the improved model, and this ref is the original model. I'll get to this part, but let's focus on this part over here. I want to get rid of all the purple in this equation. So how do we do it? Turning rewards scores into probabilities is what the Bradley-Terry model is, which is really the softmax. Give me a thumbs up if you've seen the softmax before, and feel free to give me a thumbs down if you haven't. Perfect. Okay, you've seen. So Bradley-Terry model is really the softmax because we have. I want to turn rewards into probabilities. So for example, if I have my input and my two outputs, right? The X is the input and the YW is the winning output and the YL is the losing output. And let's say that the scores are 5 and 2 because the model returns a 5 and a 2. The model that mimics the human would give it a 5 and a 2, or the model tries to mimic the human, giving them a 5 and a 2. And I want to turn those into probabilities, and I want to turn the 5 into a probability 0.95 and the 2 into a probability 0.05. How do I do that? Well, using the softmax. I'm going to take these 5 and 2 and turn them into two numbers that add to 1. So one standard trick that we use in machine learning is that we turn this into e to the 5 and e to the 2. Why? Because why don't I just take the 5 and the 2? Because these numbers may be negative. And I want to turn everything into positive. So I take, instead of 5 and 2, e to the 5 and e to the 2. That makes them into positive numbers that are much higher if it's a 5 than if it's a 2. And then I divide by the sum of the 2 to make them add to 1. So that's how I turned the 5 and the 2 into probabilities that add to 1 and that are positive. Okay, this is exactly the softmax. So the Bradley-Terry model is pretty much the softmax. So that's how I took the purple scores and turned them into blue probabilities, which is what I wanted, right? So basically, when we go here and we say, I don't like this R is a score. I turn it into probabilities and they look more like probabilities, and now I'm training the policy model. So again, this formula has too many annoying details, but if you only think of it as I take the scores, turn them into probabilities, that's how I remove the value neural network from the equation, and I only train the policy neural network, which is Omit's suggestion over here, right? Like, why do we have two networks when we can only have one? Okay, so now there's another thing we do. There's another thing we do a lot. And this will happen in many models. So remember this, because in RL, you will see this a lot. Every time you see this KL divergence here, probably what you're doing is making sure that the model doesn't change too drastically too quickly. You try to be slightly conservative in your trainings. You want to be slow. You don't want to make drastic moves because you assume that you have something good. And I'm going to give you a scenario, right? Let's say that you have a test, okay? You're helping your friend study for a test, and this is the scores in the questions, okay? These are the scores in the question. So very well in question 1, very well in question 10, so on question 7, not so good in question 6. And then we help our friend with only one question. We help them with question 7. We say, okay, listen, let's study and take the test again and do better in question 7. Okay. So the improved test number 1 is this one over here, where the student did a little better on question 7 and very similar on all the other questions. Okay, it didn't change the other questions very much. And the improved test number 2 is this one that changed everything, changed all the answers, but it did a little better, but it did a lot better on question 7, right? Sorry, problem here. Is this clear? This one did better on question 7, but it changed all the answers drastically. Okay, so the question is, what do you prefer? Do you prefer the exam that did a little better on question 7 and kept the other answers similar, or the one that did a little much better on question 7 but it messed up all the other answers? What do you prefer? I'll take votes. Hmm. Amit says improved test 1, right? And I agree, because if we're training a model and we trust the model, so don't forget that the model that we starting with is the trained transformer. We trust this model a lot. I would not want to change all the answers to all the other questions. I kind of want to get better at this and only that. So even though the model did this model did a lot better in question 7, I still trust this one. I still trust improved test 1 more, because I assume that it's doing well on all of them, and I want to get a little better in question 7, but I don't want to mess up question 1 or 2. And so, but if I'm grading the exam on question 7, I have no way to tell. So what I have to do is, this one did better in question 7, but this one's more similar to the original test. So I'm going to measure how much the test changed. And if it changed too much, that's a punishment, okay? And I use that KL divergence for that. Give me a thumbs up, thumbs down if you've seen or not seen KL divergence. I'm not gonna get into details of KL divergence, but the idea is that if my original policy is this, and my answer is x equals 3, I can improve this in 2 ways. I could get a model that's very similar and has a higher score for x equals 3, or I could change the model completely and get an even higher score for x equals 3. But if I trust this model already, then I'd rather have the similar one than the different one. Okay, so I don't want this model to win. I want, oh, I made a mistake here. Oh, sorry. I made a small mistake. Uh, it's really this one that wins. Hi. So I want a similar model to win, even though candidate 2 scores better on the actual answer. I want this one because I don't want the answers to change so drastically. This one kept them very similar. And so what I do is I calculate the KL divergence. The formula for KL divergence is something like summation of PI logarithm of PI. I have a video on that if you want to. Oh, but I see everybody's giving me a thumbs up. So this is a very educated crowd. So I don't need to explain what KL divergence is, but I can tell you, if you subtract the KL divergence times some small coefficient, because everything you do in machine learning, you want to put a small coefficient on it. Then I want the low KL model to win. So therefore, I have this, right? This, forget about this bilateral mark. This formula over here tells me you want to maximize the rewards and you want to minimize the difference between the two models. And that's why I subtracted. So this is my punishment, right? Like how well you did in the rewards minus how much you changed. Okay. And the idea, I'm not going to get into many details. The paper gets into the mathematical details in a painful way, but the idea is that if you put together the original equation for PPO, the Bradley term model, the KL equation, you end up with a loss formula, the one what Amit suggested, which is only for the policy model. So DPO basically does a lot of math to take a loss function that has value and policy and turn it into a loss function that only has policy, and then you can only worry about training the policy neural network, which is the transform. You can forget about the human. The human value neural is somewhere here embedded, but we don't need to worry about it very much. And as you can see, this thing turned into probabilities divided by another probabilities, and so on and so forth. This is a mess. But this came from DPO and getting rid of the reward and turning it into probability. So yeah, as you can see, this maximizes the probability for the good response. This minimizes the probability for the bad response, because you're subtracting this minus this, which is you want the probability of the good response to be higher, the probability of the bad response to be lower, and that's why I'm subtracting here. And that's why I have a negative sign. And you're dividing by this because you don't want the model to change too much, okay? And this is just the usual expected value that we do on over-generated responses. And you take the minimum of that. So you take a negative here. Anyway, so this is basically what you do with direct preference optimization. You have your two models, model and policy, and you turn it into only the policy neural network by doing this game. Any questions on this? We're actually doing quite well. We only have GRPO to finish. Any questions? Everything makes sense? Or any doubts? All right. So GRPO, the big boy. We're getting into the one that turned DeepSeek amazing. That made DeepSeek beat ChatGPT pretty badly, because DeepSeek is made a huge impact, not only in how model reasons, but also how small it is. You know, ChatGPT has like 1 trillion parameters, and DeepSeek has like a billion or something. It fits on your computer. You can actually download it and make it fit on your computer. This is insane. And basically, this uses a reasoning model. So what's a reasoning model? Well, I use DeepSeek for math, basically, for all my math and reasoning. Because let's say I say solve for x in the equation 2x plus 4 equals 10. And the solution here would be 3, I believe, right? Because 2 times 3 plus 4 is 10. I'm going to give you 3 solutions, and you're going to be the human. You tell me what's better. Solution 1, x equals 6. Solution 2, x equals 3. And solution 3, subtract 4 from both sides, get 2x equals 10 minus 4 equals 6. Divide to both sides by 2, get x equals 6 divided by 2 equals 3, and answer x equals 3. So who votes for solution 1 or solution 2 or solution 3? Put it in the comments. Let's see. Which one's better, 1, 2, or 3? Perfect. Benjamin says 3. Alireza says 3. Hossein says 3. The other Alireza also says 3. Perfect. Okay. Obviously, yeah, 3. Good job. 3 is the best one. And solution 1 is the worst one because it's plain wrong. Solution 2 is okay because it didn't show its work. And solution 3 is the best one because it showed its work, right? So solution 3 wins. Because what I want to do is I want to tell the model, hey model, don't just answer the question. Give me the steps. Okay, so here's a main idea. Here's where DeepSeek did amazing. Okay, um, DeepSeek and ChatGPT both did a particular thing to be able to solve a mathematical problem. And what ChatGPT did is called self-supervised learning, which is it hires a bunch of experts, a bunch of math experts, and makes them solve the problems using steps. So it says, okay, you 100 people solve the problem using steps. This is very expensive, right? Like this is a lot of people. Um, and then you feed them into the model using pretty much supervised learning. And I'm oversimplifying this, by the way, but you take the solutions, feed them into the model, and then the model basically learns how to solve math problems using steps. That's good. Expensive, but good. What DeepSeek did is it kind of duplicated itself, and it used one model to be the student to come up with solutions and another model to grade them, a combination of things. There were some heuristics. There were some, like, for example, a compiler to check out the code, a math engine to check out the math. Like, it wasn't just LLM, but it used a pretty solid way to grade each step and to grade the whole solution. And then it basically used reinforcement learning to improve the solution and improve the solution and improve the solution. Okay. And this can get much better. I like to use the analogy of chess, for example. Let's say you want to make a machine play chess. How is it that machine started playing good chess? Well, if you give it a lot of games that already are done, that's how the old machines played chess. You make a bunch of grandmasters play and feed that to the model. That's supervised learning, right? Instead, if you take the model and make it play against itself, that's when the model gets good, because the first model, the one that's trained with grandmasters, can only be as good as the best grandmaster that's already training it, whereas the model that plays against itself can reach heights that humans haven't, right? And that's how Deep Blue beat Kasparov, and that's how the AlphaGo managed to win at Go. Go is such a hard game. Like, it's so much harder than chess. So, I mean, in terms of like the number of moves there are, it's more than the atoms in the universe. But with reinforcement learning is how you manage to win at Go and create a place that a human hadn't discovered yet. So making a model play against itself is the way to reach higher heights. And here we're using the fact that models are not very good at creating. This model is not very strong, the one that creates, but they're very good at understanding stuff. A model can grade a math exam very easily. It cannot produce new questions. So we're using the fact that these models are very strong to understand stuff, maybe not so strong to create, to be able to improve the creator. Because these models create one word at a time, right? They're basically nearsighted. They can only walk to the front very slowly, but they can look back pretty big, because you can put a lot of stuff in the input of the model. So you're using that strength. Their models are better understanders than they are creators. So here you're using the understander to enhance the creator. And so basically what you do is you have to have a way to grade each solution in a way that gives you a loss function. So we're going to take the grading of a solution and turn it into a loss function and train GRPO like that. So I'm going to give you 3 solutions, and I'm not going to make you go through all of them and vote. But the idea is that solution 1 is completely wrong. Every step in solution 1 is wrong, and the answer is wrong. You shouldn't do this, you shouldn't do this, you shouldn't do this. Solution 2 gives the right answer. So this gets a bad score. Solution 2 gets the right answer with a wrong step. So this one's so-so. And solution 3 is perfect. Perfect step, perfect answer. So this gets a good score. How do we score them? Using this behemoth of formula here, which is ugly. But you can see a lot of things we've already seen, right? Look at this. It's a ratio of probabilities multiplied by a gain. We've seen that. We haven't seen the clip. Clip is very easy. I'll show you in a minute. And here's the KL divergence. So this formula may look ugly, but we've seen every single element of this formula already, except for the clip. So here is the average over all responses. So if the computer gave me 100 responses, I average over all of them. This thing is an average over all the steps of the response. So the solution has 10 steps. I'm going to take the average over all these 10 steps. here is, we already saw this. This is the probability of the new response over the probability of the old response. So you're using that momentum thing, the kid running, and I push it in the other direction. That's it, right? And this is the gain that we multiplied, the quality of each step of the response. This is when we normalize the scores. A little bit of math I'll show you in a minute. This clip, we haven't seen it, but it's very simple. I'll show it to you in a second. And then this is the exactly KL divergence that the model doesn't deviate too much from the previous one. So everything in this equation we've seen already, right? But let me go through the stuff that's new. So this A is the quality of each step of the response. So basically, what we do is we just come up with a rubric, right? We have, for example, we have a rubric for the solution and a rubric for the steps. And I'm simply just going to say, that a bad step is minus 0.1, a good step is plus 0.2, a bad answer is minus 1, and a good answer is plus 1. I came up with that as a professor, right? As a teacher, I just came up with that rubric, and I give it to each one of the steps. So now when I add them, I get the score for each solution. Very simple, right? Now, I actually don't want those numbers. I want them normalized. What does it mean to normalize? I make all these numbers have average 1, average 0, and standard deviation 1. So I basically subtract the average of all these numbers and then divide them by the standard deviation, and I get this. So you always want to do that. You normalize things, and that's why you put this hat here. So if my average of the numbers is 5, then I subtract 5 to everything, so I get things that add to 0. And if my standard deviation is 2, then I divide by 2, so I get something with norm 0 and standard deviation 1. It's the first thing you do with every data set you do. It's just you normalize it. So this A hat is normalizing, right? And so that's the A, right? That's the gain. The gain here is the score, the average normalized score of all the steps in the solution. This we know is probability of old response. This is the kid running with the momentum. Why do we divide probabilities? Exactly because of that. What is the clip? The clip is very simple. So here's something that happens. When you divide probabilities, you get into some weird zone because probabilities are small numbers. And if I have something like I'm dividing by a tiny number, this thing can really blow up. I could get 1,000,000, right? I don't want to throw 1,000,000 here because that's like throwing a wrench in a machine. It breaks everything. So I just clip them. And I say, for example, I pick an epsilon 0.1, and I say, if anything, if the number here is too big, fix it into something. If it's too small, fix it into something else. So if it's 0.1, if it's bigger than 1 point, if it's 10, make it 1.1. If it's 0, make it 0.9. And if it's in between, keep it. And that clipping actually makes your network manager. But it's not perfect. It throws a huge nonlinearity into the equation, but it makes sure you're killing high numbers that are too high and too low. Because whenever you have a range of probabilities, you should do some kind of clipping at least. Ratios of probabilities can go insanely big. If the denominator is too small and the numerator is not that small, it could be huge. So clipping is always important. And finally, this model doesn't deviate too much from the previous one. It's exactly this thing we did with the KL divergence, right? I want to make sure my model doesn't change too much from one iteration to the next one. So yeah, so this ugly formula turns into something nice. And I think we're done here. So we did DPO, PPO, GRPO, and RLHF. And obviously, I skimmed through a bunch of details, but I have 6 videos. PPO, proximal policy optimization, RLHF, direct policy optimization. I have one entire video on KL divergence if you want a reminder, and a video on deep reinforcement learning, which actually shows the whole basics of reinforcement learning, policy gradients, the Bellman equation, and this is the last one, GRPO. I'm in the process of changing my thumbnail, so I haven't changed them all, so that's why they look like 2 different styles. But yeah, we have basically, I encourage you to take a look at my channel, Serrano Academy. I'm gonna type, I don't know if I typed it already, but I'll type it again. And there you can find the whole, there's a playlist with all this reinforcement learning stuff. But yeah, other than that, thank you for your attention, and I'm here for questions.
Thank you, Doctor. It was a great presentation, and
Thank you.
thank you for that. So we are opening for the question. If you want to ask question, please raise your hand, and I can give you microphone and webcam access.
Feel free. Yeah.
So we're waiting to see if people want to ask question.
Please, in the meantime, I'm gonna search for a playlist that I have because I did put all these into a playlist. It's called Reinforcement Learning for LLMs. Here it is. Yeah, I'm gonna share this with you, and by all means, check it out, and it's basically
And
the same thing I said, but extended to like I don't know. I think I'll do each one's like half an hour, 20 to 30 minutes. So this is a fair amount of information. Yeah.
thank you for sharing it. Until people come up with question, can I ask a question myself?
Oh, please.
Okay,
Yeah.
okay, okay. I want to ask about what do you think about this current wave of AI that we build a giant prediction machine and we do all on top of it, and then we try to answer everything with them, and they make a community of agent and try to do synchronize this community of agents in a way that they can answer to questions that none of them could answer
Uh-huh.
itself. I want to ask you, what do you think? Do you think this trend would plateau in someday in the future, or do you think it goes on and on and on? What do you think is missing in a way that we want to reach super intelligence? We want to go beyond our understanding, or maybe we want to mimic the natural intelligence. Is there something
Yeah.
missing in the picture, or do you think that's the
That's
way?
a very good question. Uh, I think we need to redefine intelligence because I think these models, if they're not already, they have no limit in how much they're gonna beat our intelligence. I mean, if they beat us at chess and at Go and in math Olympiads or things like that, like the hardest the IQ tests and the Turing tests, like I think trying to be smarter than a machine is gonna be like trying to run faster than a car. Like you can't. Um, I think there's an every time there's still us. Like I think we're still gonna be relevant, and we just need to find the places where the machine is unable. So I think I think we have a lot of creativity. I think we're still use these tools. We should use these as tools, not let them make decisions, because a human decision takes a lot more than intelligence. It takes a lot more than just numbers. You could make decisions using only numbers, but you're not going to end up that good, because imagine living your life only looking at numbers, right? Be like, okay, I'll make the decision that makes me get a higher salary and make the decision that makes me, at the end you end up miserable. You know what I mean? Like there are some key decisions you take in life that don't match numbers. That's where we come in, right? So I see, for example, I see at least two places where we can come in, like emotional intelligence, for example. A machine does not have that. A machine is just numbers. Any AI model, as a matter of fact, let me just even iterate this. Any AI model is some complicated formula that you're maximizing or minimizing. Whenever there's not that, there's some kind of emotional intelligence. There's empathy. We don't. The computer has no empathy. There's no room for empathy in this formula, right? Intuition, when you have an idea that you think you should follow, like that kind of stuff is where humans come in, not in the math. We have nothing to do in the math because the machine beats us already. So I think we need to explore those places as a human race, and maybe end up focusing on those and have the machine do our rational thinking. So I think that's where it plateaus in the sense that they're going to be smarter than us, but we need to take the decisions and feed them into the machine and use them as tools. We should never use them as decision makers. Yeah.
Don't you think we can also formalize those kind of things, because we get this information into our senses, it somehow transforms in the physical world, and we make decision about our emotion. Don't you think?
Maybe. I think so. This is where this idea came up. I was working at YouTube for a recommendations team, and the goal, the dream that we had was to be able to measure what's a good experience, right? So for example, it started with, are you likely to click on a video? If you click on a video, means you like it. but that's not true because we click on a lot of garbage that we don't know. Like the thumbnail can be. So we changed it to how much time you spend watching the video. And that was a better metric because a good video means you spend more time watching it. But that's not a metric for how much time you had. You could have had the best time of your life or a horrible time, or maybe it video triggered something wrong and it would just ruin your life. Like the fact that you watched it for 5 minutes says nothing, right? And so we started trying to fit the numbers, and we were like, okay, maybe the probability of clicking times the amount of time you watch it times the amount of time you watch the next day times the number of videos that you watch. And no matter what you try, there's no way to quantify a good experience. Likes, comments, sharing. There was, of all the things we tried, we never even got close to telling apart if you had a good experience based on numbers. So that led me to believe that numbers don't tell the whole story. Like there are things that are not measurable by numbers, and AI can only do things that are measurable by numbers, no matter how complicated, right? Like these are all things that are measurable by numbers. So I have the belief, and I have no proof of this, but I have the belief that most things are not measurable, but not only that there are things that are measurable, but I think most things are not measurable by numbers. And we come in there. We the qualitative, anything that's qualitative is hard. If I want to be, for example, as healthy as I can, like there are some numbers, but I can't just guide by those. There's or I have to change them, right? Like first is the weight, but then it's like I have to have some kind of intuition to decide what numbers to go for, because if I only try to reduce my weight, that's not a way to get healthy, right? So deciding what metrics, changing the metrics, using different ones, stopping to use one metric and changing to another, that's a qualitative decision. And I feel like humans are better at solving qualitative problems. Anything the computer does is quantitative, and it could be that we find the quantitative solution to everything, but I doubt it, but I have no argument, right? I just think it is.
Okay,
Yeah.
okay, okay. Thank you for sharing your thought with us.
Yeah.
Let's see other
You can
place.
get
But
philosophical pretty quickly when talking about
yeah,
AI.
someone asking something in the chat. Uh,
Oh, it's a great question by Amit. Is GRPO applicable only to reasoning? That's a good question. Think, I think it's used mostly for reasoning, right? Because this formula is pretty much tailored for reasoning, right? Because you have steps. These are the steps are T, and you have a bunch of steps and a quality for each step. So I think of it as a way to. It's definitely catered for reasoning. But anything that has steps, you can use GRPO. So in principle, for example, I don't know. I'm just like talking out of my I'm thinking right now. But if you were to tell a story, for example, you could analyze each chapter and grade the chapters. So anything that you have like sequential thinking. So it doesn't have to be reasoning. It can be a poem or something. It can be anything that's sequential. Anything where step one follows, then follows step two, then step three follows, and step four, and the steps follow from each other, and you have a final thing. So anything like that, GRPO is built for. I don't know if it's just reasoning, but it could be any kind of sequential thinking. So I'm gonna basically, yeah, what I'm thinking is yes, reasoning is the top, but a GRPO is built for sequential thinking. And anywhere you can find sequential, is GRPO is good. Yeah. Any other questions? Ah, Amit says, will we see greater use of GRPO in LLMs? Is it a promising field of research? I think my answer is as good as anyone's. I do think it made a huge impact. I think it was a good. It's very refreshing to see a step that is conceptual as opposed to put more machines, because normally the answer is throw more machines, get a bigger model. I think GRPO was a really nice conceptual step. So I think we haven't yet get the best out of GRPO, but who knows? I think it could be that we come up with something better, or it could be that they get more out of it. I feel like there could get more out of it because GRPO was used by DeepSeek with a lot less computing power than OpenAI and got as good or better. But I don't know what happens if you use GRPO with a lot of computing power that OpenAI has. So I don't think we've completely squeezed every single drop of power out of GRPO. There could be a lot more. Um, and if it's a promising field of research, I think anything is as good as any other field of research because anything could go up or down. But it could be that if GRPO, it could be that if you're thinking about researching, for example, like if you're researching GRPO and it turns out that you find something better, or you continue working on GRPO. So like it's as good as field as research to continue. So I would just say whatever you find interesting is a good field of research because either you find something better or enhance that, right? But I would put I would if I was me, like I was a researcher, I would put energy on that. Yeah. Thank you, Amit.
Hello,
Is that
Prof.
you? Okay.
Um,
Hi.
Thanks for your talk. It was great. We kind of wrap up the RLHF in 1 hour. I wanted to ask you about about these sections of AI. Like we have reinforcement learning, supervised learning, and unsupervised learning.
Hmm.
Like which part do you think is going to have the most impact in the future in terms of the value and the novelty it can bring to the AI community? And also because like for me, because I'm as a data science students, we study lots of these topics like RL course, machine learning course, deep learning course, and it's a very vast and diverse topics. Like where do you
Hmm.
think we should focus on most, and like in which application area? Because also AI can do multiple things, like in
Yeah.
genetics, in transportation, like which part should we like get into to really focus on and to really can bring value?
Hmm.
I'm really
Oof.
confused.
Wow, that's a very good question, Omid. I
Thanks.
would at least let me answer the second one first. Anything that's good for the world. I mean, I feel like these models are used for negative things, and I would say anything that's good for the world, I would put energy on that. Because yeah, I mean this is a beast. Like this piece of technology can really do a lot of damage. So I would just say that decision of that is just whatever you want from the world, like whatever world you want to live in. That's where you should put your energy and you should focus AI on. Enough people are focusing on doing bad with it. So I think uh, that answer is just it's just whatever you find good. Um, as for topics, that changes all the time. If you ask me tomorrow, it's a different story. Reinforcement learning was kind of dead for a while. Like people were like, "Who does reinforcement learning? Nobody cares about reinforcement learning." And then all of a sudden, our lead chef came. So I would never write something out. I think there was a quote actually by what's his name Jan LeCun a few years ago where he said that if it's a cake, then the cake is unsupervised learning and the cover of the cake, whatever the is supervised learning, and the cherry is reinforcement learning. And I think what he meant to say by that is that unsupervised learning is the big thing. I agree with at least that part. Not that the cherry is RL, because RL is way more important than just a cherry, but unsupervised learning is the fundamental, in my head, the fundamental AI, because it's trying to understand things, just trying to generally understand them. And generative AI is a part of unsupervised learning, right? Generative is because supervised you have the answer, right? You want to check if something is X or Y, or yes or no, uh, spam or not, or something. So supervised is more straightforward. Unsupervised is kind of like more open. It's trying to understand your data. So that one's never going to go away. Like unsupervised learning is never going to go away. So definitely learn a bunch of that. Um, but I would say, if it's an area if it's of learning, you need to learn all of them, like supervised and supervised and RL. You can't go wrong with all of them. Um, but if it's yeah, for areas of research, I think everything has the same possibility of being big or not. And I would say if you just focus on whatever you like, that's the only thing you can do. Like focus on the one you like the most, and if you have a good understanding of AI, you'll be able to switch around, and be working on what you like. I'll give you an example. Like I started working on quantum AI at some point. I thought it was the coolest thing. Then it of quantum computers. It kind of slowed down a little bit. It may pick up again, and then so I just kind of switched to LLMs was a big thing. So I switched to working on LLMs. You can always switch around if you know the basics well. So yeah, that was a lot for a non-answer. I don't think I answered the question at all.
Yeah, yeah,
Yeah,
you kind of answer like about the second one, like you go for the things that you like. I think like it's mostly true because you can do basically anything with AI. So why not focus on the
yeah,
things that you basically like? For
yeah.
example, for me, it's like I have a little interest on genetics and genomes, like how we can
That's where you should
help.
go.
Yeah,
Yeah,
so maybe I should go for that.
yeah,
Uh, and about the first part, I think like in my opinion, I think like for the supervised learning, right? Like I think we have more creativity on the RL part. Like at least for the supervised learning, like it's like
yeah.
something that's like as you said in your examples, like if we have a supervised things and if we have labels, we can only reach to the level of the expert. Only we can
Yeah,
reach the level of the
exactly.
labels. But with
Yeah.
RL, we can see that we can have these adversarial matches
Hmm.
and some kind of beat the labels and be better at the labels.
Yeah,
Uh,
exactly.
so I'm totally agree with you on that. Yeah.
Great, thank you, Amit. Yeah, no, and as you see, like in history, like things change, right? Like they were doing supervised, and then somebody said, "I'll do RL and do a lot better," and then somebody said, "Oh, I'll take your RL and do it supervised with DPO and do better," right? So like these things are you need to have a working knowledge of all these things to be able to say, I improved with RL and now I improved. Like this is not a this is I try to be more of a generalist than a specific. And if a field some stops growing a little bit, you can switch around a little bit, or always remembering what you know. And so yeah, I take the generalist approach a bit more. It's I think it's healthier.
Yeah, yeah, yeah.
Yeah.
Thank you for the answer.
My pleasure. Thank you for the good question.
Uh,
All
th-
right. Yes. Hi,
Thank you
Ash.
for your great presentation. If we have a few minutes, I'd love to ask a closing question.
Oh, sure.
Sure. Okay. I want to ask, what's your general advice for the people who just start their AI career in 2025? If you want to be a researcher,
Ooh.
something cool. I want to know what's your advice for
Oh gosh, yeah, that's a good
people of this
question.
class just exposed to the RL and have deep learning courses and machine learning courses before, and they just want to start and their research career or want to do something cool.
Yeah, I mean, for a full beginner, this class, I think if you every time they gave me a thumbs up when I asked a question of how do you know, so I think this class is quite advanced.
Uh,
For a full beginner, I would say go for. I would say the same thing. I mean, when I started learning AI, it was well into my 30s. I was a mathematician before, and I started learning late. But it was like 10 years ago when the AI was kind of like becoming a thing. Um, I just started looking at data sets that I liked. So, for example, there was like a tennis data set. I started plotting it and looking at trends, and maybe if I see a line, then I would just learn linear regression. So, I think the best way, I think you have infinite energy when you're doing something you like. And I think if you pick a topic that you like, a topic that you enjoy, and that you think the world, like if it helps the world, you can go from there and be learning the stuff you need, right? So for example, me, like it's interesting in genetics. You start studying genetics and what AI you can do in genetics, and then it turns out that you need to learn a Markov model because genetics have that thing or something like that, and so you go and learn it because you need it for that. But it's fun because you're thinking of solving your problem. So I think if you have a horizon, like a problem that you want to solve, and you learn all the AI from there, I think that's the best way to go. And yeah, and I would say just remove the guilt. We have this guilt. Everybody that I know in AI has thinks, oh my God, I don't know the whole thing. There's like entire fields that I don't even know a thing of, and I just feel so behind. And it's like, but everybody feels like that because it's a huge field that changes all the time. So you can't know it all, and you just have to not feel guilty about the stuff you don't know and feel good about the stuff you know. And that goes to um, ways to think as well. For example, I'm very bad at coding. Terrible. You see, my talks have no code. Yeah, that's explicit. That's I can code basically, but I tried to be a programmer for a while, and it couldn't work out. Some people are the opposite. Some people are great at coding, and they don't do so much analysis, but they just do like the ML ops like crazy. And so you also pick what's your side of it. And I don't feel any more guilty about not coding, even though I did feel guilty before. But some people do that, and I do the talking, and another one does the analysis. So like it's you just gotta be comfortable in doing the stuff you like, the way you like it, on the problem that you like, and don't worry about trying to touch all the possible fields. That's impossible. And if something comes up super big, then we all learn it. Like LLMs came in, and all of a sudden everybody started worrying about NLP, even if you have never worried about NLP before, because you just follow big trends, right? um but yeah, just remove the guilt. I think if you just constantly remember to not be guilty about the stuff you don't know, that takes a huge weight off your shoulders.
Thank you. I think it was a
Yeah.
great answer to my question. Thank you.
Okay, I take a long time with my so you give me good feedback for my answer. Means I gotta train my policy model to answer more like that.
Yeah. And you train our policy
Hey.
network for all of these holdings.
Perfect, yeah.
Thank, thank you.
All right,
I think with
yeah, thank
that
you.
we can end the session, and I want to again thank you for accepting our invitation and giving
Okay,
us
thank
this
you.
great talk. We are very excited to have you with us today.
Thank you for the
Thank you.
invitation. I'm very happy
Thank
to be in this class and happy to stay in touch. And yeah, you have my
thank
YouTube,
you.
and you can find my LinkedIn as well. I'm just gonna put it here if
Sure.
anybody wants to be in touch. I think it's this, but if it's not, it's something like similar.
Thank
And yeah, I'd love to stay in touch. Thank you for the invitation. And Jorafes, is that well said? Jorafes,
you.
how do you say bye?
Yes.
Jorafes.
Khoda Hafiz. Khoda
Khoda
Hafiz.
Hafiz. Okay,
Yeah.
thank you. I'm perfecting my Iranian.
Thank
That's also for the policy.
you. Yeah.
My Persian. All right, thank
Great.
you everybody. So happy to be here, and for the great questions. And yeah, we'll see you
Thank you.
next
Thank
time.
you. Have a good rest
Bye,
of the
Harsh.
day.
Thank you so much. Bye. Have a good night.
Thank
Bye.